So let's figure out the.
Okay, before I turn off the lights, so how did you guys do on the midterm? I didn't grade it yet. Was it good? Was it hard? Well, I didn't grade it, so I'm gonna take it from the TA today, and I'm gonna grade it today. But I believe most of the stuff are from homework, and I gave you an idea last time, right, on the board, right? I helped you in 25 points. So if you got what I did on the board last time, you would solve at least one of the questions, that the superposition, right? I believe the most difficult one is the arch one. It has a little bit indirect way to get the reaction. So if you figure that out, so you'll be able to figure the problem. This is, I believe, the only, I don't want to say trick, but the one that needs a little bit of thinking to get the reaction. That's the only one. Other than that, the whole homework. I have to put some little or some questions or some little tricks so I can distinguish who's A and who's B and who's, so that's how it works. Okay, so, and it's not that crazy, all right? Okay, so today or in the next, I believe, 3 weeks, actually more, maybe a month. So we are gonna study the analysis of structures using software. So as I said last time or last week, we are gonna do SAP 2000, and then we are gonna do ETABS, and then I'm gonna introduce the course project that we're gonna work on, right? So I don't think that you guys can see the screen, so maybe we do this. Can you try this one? I think this is much better, right? Okay, so what I do when I teach structure analysis using software, or I believe most of the courses that teach structure analysis by software, they have to start with something simple. Something like trusses, 2D frames, beams, and then we go to slabs, and then we go to a whole building analysis. So that's what I'm gonna start you with. We are gonna try to solve this truss. This truss, actually, you can solve it on your own. Like, it has dead load, it has live load, and then you can solve the dead load separately, you can solve the live load separately using the truss structure analysis basics that you learned. And you can get the reactions, and then you can get the normal forces in each one. So right now, I'm gonna teach you how we can do this in SAP 2000. And I'm gonna use this example as a way to introduce SAP 2000 to you. Like, I'm gonna spend maybe an hour explaining this truss, but actually this truss can be solved in 2 minutes. But I'm gonna spend an hour because I'm gonna introduce every aspect of the software while doing this truss. So I have your full attention and your full focus while I'm doing this. Okay, so all right, so as I said before, for SAP 2000, you can use the version on Citrix to use it for this class, or you can download the trial version. And I believe we're not gonna spend over months on SAP 2000, so you can download the trial one right now, and you can start using it while we're doing this class. I believe we only have 1 or 2 homeworks on SAP 2000. That's it. All right, so when you open it, SAP 2000 screen, try one thing. Okay, so this is the SAP 2000 screen. Mainly, that's what we are interested in, is the tabs up there. Because if you know every aspect about these tabs, you know the whole software. So as any software like Word, Excel, or any software you are gonna have the file, edit tabs. The file edit tab that manage the files. If you wanna open file, if you wanna open a new project, save a project, that's in any software that you do, you have a tab that's called file. So let's go on file and see what we have. So when I go to file, basically since we have a blank screen, there is not a lot of options. Like if you have a project that is already, that you started, So you're gonna have save, you're gonna have save as, you're gonna have a lot of these are activated. But since we are starting a new project, so we are gonna start with something new. So I'm gonna hit new model. And once I hit new model, the SAP 2000 is gonna help me a little bit. It's gonna say, hey, I know that you are gonna start a new project, but let me help you. Do you wanna start a blank screen, like a blank that doesn't have anything to start with? Or do you want me to build some grids for you so that you can draw your structure easily? Or you can choose one of the templates that I have. Maybe you are doing a beam, I'm gonna help you draw the beam very fast. Just give me some information about the spacing, about the boundary conditions. I'm gonna start it for you. Same thing, trusses, 3D trusses, 2D frames, 3D frames, walls, even stairs and tanks. So, and that's actually what is good about SAP 2000, that provides you with a lot of options, and it can do analysis for any structure, which is different from other softwares, as I said last time, that ETABS 2000 is only, or it's the best to use for what? Do you guys remember? ETABS is good to do structure analysis for tall buildings, multi-story buildings. There's a safe is only for slabs, but SAP 2000, it can do, like if you have a swimming pool, I would do it with SAP 2000. If I have a retaining wall that holds soil behind it, I do SAP 2000. If you have a tank, I do it with SAP 2000. If I have a stair or a spiral stair or all these, I would do SAP 2000. Till now, if I get any of these projects, I would use SAP 2000 for that. But if I got a tall building project, I forget about SAP 2000. It's not good for tall buildings projects. I would do ETABS, and that's actually what we use in most of the design firms. Even like Burj Khalifa in Dubai is designed using SAP 2000. Most of the tall buildings that are out there, it's done by ETABS, not SAP 2000. Okay, so for me, I'm gonna do this truss using grid only. I'm gonna teach you how to use this tool. So, but before I do this, I have to do some stuff very quick. I have to tell SAP 2000 what are my units that I'm gonna use. I'm gonna look at the AutoCAD file that I have. I have the distances or the spaces are in meter and the loads are in ton. So what I'm gonna do, I'm gonna go to SAP 2000 and I'm gonna pick that my units are ton and meter. So if your units are kips and inch or kips and feet, you use kips and inch and feet. So the first thing that you have to do in any structure analysis software is to pick the units. So I'm picking ton force meter, and I'm gonna tell SAP 2000, hey, I'm gonna start with grids, and I want you to help me with that. Sorry, I forgot to record the screen, so let me record to the cloud. All right, so here, this is the structure that I wanna solve, and I wanna use the geometry that I have on AutoCAD to start building the grids. Let me ask you, this structure is an XY or an XZ? XZ, that truss is going up there, like this, not a plane structure that an XY direction. So tell me, how many grids do I need in the X direction, and how many grids do I need in the Y direction to start drawing this structure? Can you tell me? Grids, that means line that can help me draw elements from line to line. Because the thing is, the intersection between the grids, I'm gonna use it as a big point to draw a frame element from a point to another. Like if I wanna draw this frame element, I want to have a grid here and a grid here. So can you tell me how many grids do I need in the X direction and in the Z direction?
5 in the X and 2 in the Z.
Exactly, excellent. So I have 1, 2, 3, 4, 5. And in the Z, I have 1 and 2. How about Y? How many grids do I need in the Y direction? 1, not 0. Why? Because you have to start with something. You have to start with 1, but there's no 2. Okay? There's no such a thing as a 0 grid. There's 1. Okay? So let's go to SAP 2000, and I'm gonna say number of grid lines in the X direction, we said it's 5. In Y direction, we said it's 1. In Z direction, we said it's 2. How about the spacing between the grids? So I'll go back to AutoCAD. I have spacing in the X direction at 3. In the Z direction is 4.4. So I'm gonna go here. I do a 3. And And here it doesn't matter if you put 6, if you put 10, it's only one grid. So, and here I'm gonna put 4.4. And it says, where's the grid line location? Basically, the last one is asking you, do you want the grids to start from 0, 0, 0, from the origin, or you want to put them at the specific origin? No, I want them to start from 0, 0, 0. So then I'm gonna hit OK. Let's see what's gonna happen. So when I do this, SAC 3000 is gonna divide the screen into 2 screens. If you want to make them one, you can make them one. But I would rather to work with 2 screens. I usually leave at one as a 3D to see how my structure is evolving, and I make one as a 2D, either XY if I'm working on a slab, or XZ if I'm working on a truss. So right now I want to draw my truss. XY is not going to help me, because I want an XZ so I can start drawing my truss. And actually that makes sense. Why? Look at here. This is, if you look at the structure from the top, you are going to see one line. But if I look from the XZ, I'm going to see my grid. So let's say I want to switch this view from XY to XZ. So I'm going to go back to the software. You're going to go here, and up there you are going to find, take this down, you are going to find here the views. You can see either, if you want to make this 3D, you just click 3D. If you want to make it XY, you click XY. You want to make it XZ, you click on XZ. Or you go to view, here, and you can set the 3D view or you can set the 2D view, but I would rather use these two. So let's say you are here, you made it 3D. So you can come here, view, and set 2D view, and then you can pick what 2D view that you want. So if you want XZ, so you can make XZ, and then you say, okay, it's gonna be X. But that's too much work. I would pick it from up there. All right, so right now I can see my geometry. Sorry, the grids, I didn't do any geometry right now. I'm just preparing the SAC 2000 so I can draw my geometry, all right? So right now I can draw my members. I can draw the truss member from here, 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 there, there, there. So let's just say I started drawing the members. I can start drawing using the members here. Like, as I said last time, or last week, we said that we have multiple elements. We have frames, we have shell, we have blade, we have membrane, but mainly what we are going to use in our career, frame and shell. If it's beam, it's going to be frame. If it's a slab or a wall, it's going to be shell. So either one of these two, frame or shell. The truss is going to be frames or shells? Frames. But let me tell you something. When you do research, sometimes we model the frames as shells or even solids. But when we do that, just like, I don't want to generalize things, but it's different when you go practice engineering in a firm and when you do research. So the thing is, when we do a structure analysis, all what I'm interested in, if a beam has a load like this, I'm interested in the bending moment. I'm interested in the shear force diagram on this beam. So frame is enough to give me all that. But frame is not like, it's not the optimal, or not optimal, it's not the most accurate representation of the beam. We are eliminating a lot of information about the beam. So when we do research and we want to investigate a lot of stresses and strains and cracking, so we model this frame as a shell. Like we make a shell like this with the same depth of the beam. And we make something like this. We divide this as a shell and we keep dividing it into small spaces and we keep studying what's going on inside the beam. How's the stress strain is developing inside this beam. Here I cannot do that much. I can, but not if I have shell. And sometimes when people want to get in depth in the analysis of beams, they make it 3D. Something is called solid element. And they make these solid elements dead, but this is cannot be done. I believe there are some solid elements, but this analysis cannot be done by SAC 2000. We use different softwares like ANSYS or Abacus, lots of research software. Okay, so research-wise, yeah, we can model the beam as a shell. Like, and when I was doing my master's, frame was not enough, so I had to use shell to model the beams. Like I was doing in in my master's, and we can discuss it in the tall buildings. In tall buildings, we have something called shear walls. Shear walls take a lot of bending moment or a lot of increase the resistance of the building. But sometimes we end up with having two shear walls, and I have to make a space between them. There's a space between them, and they are two separate shear walls. We make something called coupling beam to make these shear walls act as a one wall. Like, rather than every one moving separately, we are gonna make them feel like a one wall. So we connect them with a beam at the story level, something like this. My master's thesis was in the analysis of this beam. This is called coupling beam. It's a very, very special beam. If you model this beam as a frame element, you are not gonna see what is this beam actually doing. Like, basically, this two walls is not gonna feel this beam. So what we did, we make it as a shell element. Like, it was something like this. We modeled the whole depth of the beam. Something like this. And actually, the reinforcement of this beam is very special. It's something that's like cross, like this. Like, basically, if this is the beam is like having reinforcement like this, and reinforcement like this. All these beams to provide coupling to make these two acting together. So sometimes there's some cases, no, we cannot model the beam as a frame. But in most of the structural engineering application, since we're only interested in bending moment and shear force diagram, we model the beams and model the frames as a frame element, okay? But there's some exceptions, and we talked about them right now. Okay, so let's say I want to start drawing my frames right now. If you start drawing the frames, basically SAP 2000 is going to develop a generic cross-section of this frame. And I don't want to do this. I want to define the materials and define the cross-section before I start drawing sections, so that I save a step down the stream, because after I draw using these ones and I start drawing, I don't want to come 5 minutes later to assign new sections to each one. So basically, let's say that you have a structure, and this structure has columns that are 50 by 50, and a column that is 40 by 40, and a column that's 30 by 30. If you start drawing right away, so all of them are going to be the same cross section. I want, when I draw, I pick the dimension, the right dimension for each element. So let's see how we can define this. First, I'm going to start with define the material. So there's here a tab is called define. So I'm just going to click on define, and you are going to find a lot of things that you can define. You can define materials, you can define sections. There's something called mass source. We use it for seismic design. There's something called function. There's some, if you guys heard about responsive spectrum for designing, for earthquake engineering, we define the responsive spectrum function here. There's something called load pattern, load cases. If you want to tell the software that it is a dead load, there's a live load. So we do all this here. Okay, let's just start by defining the materials. So once you start defining materials, you are going to find that SAP 2000 has already two materials predefined for you. You can use them. However, sometimes in some engineering projects, these materials doesn't represent the materials that we have in our project, so we have to redefine the material. You either modify them or redefine a whole new material, or you can import materials that you already have on file. Some companies have their own materials and you just can't import them. Okay, so let's go in this material and see what does it have. From the name, I can see it's a 4,000 pound per square inch. About 4,000 pound per square inch, that gives me the vibe that this is a concrete. This one, it says A99 F yield 50. That means, oh, sounds like a steel. Okay, so if you want to go, you can either go modify this material. So I'm going to say modify and show material. So when I click on this, all this is going to show up. You're going to find out that the material name, it's called 4,000 pound per square inch. The material grade, it's here. But the thing is, if the name is saying that, this doesn't mean, like, let's say you adjusted, let's say if you adjusted this to 5,000 pound per square inch, and you said save. So this doesn't change the material, because all what you have, you just changing the name of the material. You can actually make the name of the material Omar, or you can make it green. You can make the material whatever name that you would like. But we would rather name the materials with unique names. Like what is the unique name? What is the unique characteristic of this concrete? Is the characteristic strength, the compressive strength of the concrete, which is 4,000. So all what I'm gonna do, I'm gonna keep the 4,000. I'm gonna check the weight per unit volume. It's 2.4. This is actually the density of the concrete, which is right. And here you are gonna find the modulus of elasticity of the concrete. And I showed you last time, if you want to calculate the modulus of elasticity of the concrete, you can do that. Like E is equal to 4,700 root FCU, the compressive strength. So if you know the compressive strength of your concrete, you can calculate this number. And the Poisson ratio, which is the relationship between the lateral strain over the longitudinal strain of the concrete, which is always 0.2. And here is something that's called the coefficient of thermal expansion for the concrete, and the shear modulus, which we'll rarely use. And here, there's some parameters for design. Here, because when you do design, you need to know what is the compressive strength of the concrete. We're not going to do design in this course, but for you, you have to know what is the FCU of the concrete, and how we can know that. We talked about it last time. When you have a truck of concrete that's coming to the site, we take samples, we break them, and we get the mean and standard deviation of the concrete compressive stress, and you can put it here. So, so that's most of the information in any material. I'm not gonna change it. I'm gonna keep it, use it the way it is. So, but if you wanna change it, you can change it. Like you can change these, and I'm gonna keep this 4,000 per square inch. Same thing with the steel. I'll modify and show. So if you are using steel cross sections for this truss, you have to define what is the steel material parameters is. So same thing, you are gonna have the material name, you are gonna have also the weight per unit volume. The steel is always 7.8 ton per meter cube, and the modulus of elasticity, and the Poisson ratio, which is 0.3, the coefficient of thermal expansion, and all the yield stress, the tensile stresses, because the steel has multiple information. If you guys remember the curve of the steel, it goes like this, and then it yields, and it goes to a maximum, and it goes to a breaking point. So here you put all the information about the curve for the steel, because that's what the SAP 2000 uses for design. For me, I'm not going to define these right now, because we are only interested in analysis. I'm not going to hit the design button over there. I'm going to only do analysis, because in this course I'm only interested in internal forces. Okay, so I'm going to keep the materials the way they are, and then I'm going to say okay. All right, so that's defining materials. Let's define cross sections. So when you go to define cross sections, you are going to find multiple things to define. You are going to find frame section, you are going to find tendon sections. If you are going to do pre-stressed concrete or something, you have to define the cross section of the wire. Or we are going to do a cable, like you have a cable, like one of the cable structures that we saw. You can use cable. The difference between tendon and cable, the tendon is the one that you put in the post, like a post tension or pre-stressed concrete. That's a tendon. But if you have a cable, that means like you have a cable stayed bridge or a suspended bridge. So you use a cable, so you have to define the section of the cable. And area sections. Area sections is the one that we kept talking about them last week. The blade, the membrane, the shell, all of them are under the area section. And there's something called solid properties. I didn't use it in SAP 2000 before. And there's a bunch of other stuff. So we're only interested in frame and area sections for this class. Okay, so let's go for frame sections. So I'm gonna go to define, and then sections, and then frame section. In frame section, you either import sections that you have already on your computer, or you can start adding a new property, and that's what I'm gonna do right now. So when I start adding new property, you can pick from the materials that SAP 2000 have. So that SAP 2000 has steel, have built up sections. Sometimes you want a section that is built up from multiple cross sections. You want to put two C sections together, and you want to build a blade under this and a blade under this. You can build your own section. Okay.
There it is.
All right. And then you have concrete sections and aluminum and whatever. So let's start with the steel. We mainly are going to use steel and concrete, and mainly concrete. So if I want to define a steel section, you can click, let's say, on the I-beam, and in the I-beam you have to define, let's say, I-500 or something. You have to define all the information about the I-beam. You have to define the outside height, the top flange width, the top flange thickness, the width thickness, the bottom flange width. Like, you have to define the parameter of each one. This flange, width and thickness. This width and thickness. The bottom flange, width and thickness. You have to define all these. And you have to pick the material. Let's say that you are going to use different materials for the different steel sections that you have. So here, all the materials that you have is going to show up here. If you define 10 materials, once you click on this one, you are going to see all the materials that you have. So I'm going to click here, and basically SAP 2000 know that this is a steel cross section, so he assigned the steel material to this section. Okay? There's something here, it's called set modifiers. I'm going to talk about these modifiers. Basically, sometimes when we design for seismic, the seismic design assume that the cross sections are already cracked to do seismic analysis, because we do something, we were going to talk about this concept. We reduce the stiffness of the whole structure. So when we reduce the stiffness of the whole structure, we make the stiffness modifiers for the structural element a little bit less. Like the columns, we reduce them by 30%, so we take a factor of 0.7 on the stiffness. The beams, we make them 0.25. The slabs, make them 0.5. So when we reduce the stiffness of the structures, we use these modifiers. And sometimes when we work, I'm not sure if you guys, maybe in the future, you're going to work with retrofitting of a structure. So you go to a 30-year-old bridge or a 50-year-old bridge. So it's all cracks everywhere. So if you want to have the cross section of the column, so you cannot use the full strength of the column. So you have to reduce the stiffness of this column. Okay? So we can do this here in the set modifiers. And there's some stuff that you can, we're not going to touch these stuff. So let's say okay. And if you want to add a new property, and you can make this property concrete, which is much more easier than the steel. Let's say we are going to pick a rectangular beam. So basically, let's say I'm going to say beam 50 or 25 by 70 centimeter. So all what you have to do, I'm going to make the depth of the beam 0.7, and the thickness is 0.25, and I'm going to make the concrete material, which is the 4,000 per square inch, and I'm going to hit OK. So that's a concrete material. Very, very easy. So look at that. I defined here that the beam is 25 by 70 centimeter, but the unit wasn't metered. So the name doesn't matter. It's just a name. All what matters is the units inside the cross section. Okay? So this is how can we define cross sections. So let's say we are done with the cross section part. I'm gonna teach you right now how to define. So right now we knew the material, cross section. So let's define load pattern. So when you start defining load pattern, you will find that SAP 2000 already defined dead load for you. Because SAP 2000 assume that I'm gonna calculate the on weight for you. Like once you draw the structure, I'm gonna calculate the on weight, and I'm gonna put the on weight in the dead load. You draw a truss, I'm gonna calculate all the steel section weight, and I'm gonna put them here. You draw a building, I'm gonna calculate the slab, the columns, everything, and I'm gonna put them here. But let's say you don't want SAP 2000 to calculate this for you. What should I do? The thing is, in our problem here, I don't want SAP 2000 to calculate loads for me. Because if I let SAP 2000 calculate the load for this, and that, this is going to act like a simple beam, and it's going to have a bending moment. And important hypothesis about the truss, we assume that the weight of the truss members is very, very light compared to the loads on the truss. Like the on weight of the truss itself, like this one is very light. So we assume that this is very light. So we make the loads of this truss is 0. And we calculate the on weight of the truss, but we assign it at the joint. Okay, like this joint is having the weight of all these. This joint is having the weight of all these. All right? So we don't want SAP 2000 to do this for us, so what should we do? So I'm gonna ask SAP 2000, hey, don't calculate the own weight of the structure. So make the own weight is equal to 0. However, I want you to keep the dead load pattern because I'm gonna assign it by myself as a concentrated load on the joint. Okay? So let's see how we can do that. So basically you come here, this is dead, it's called the load pattern name, and the thing is you can choose the load pattern type. Let's say you can pick a name for the dead load. You can name it on weight, you can name it whatever you want, but what matters is the type. So I'm gonna name it dead, and I'm gonna keep it the type as a dead load, all right? And then it says here, self-weight multiplier. So basically ask you, how much of the self-weight of the structure do you want to save it in this load case? So if you put 1, that means you want the 100% of the own weight to be saved in this load case. So if you want to make it 0, you just keep this as 0. I'm going to say 0, and then I'm going to say modify load pattern. So right now, there's no own weight that's going to be calculated in this load. But however, let's keep it for now. I'm going to keep it for 1 and say modify, and see what's going to happen. Let's say that you forget to put this. I'm going to keep it 1. Let's say how this is going to affect our analysis, okay? All right, so I'm going to keep it for 1. So what is going to happen now? What is going to happen is the SAP 2000 is going to calculate the own weight and also the dead loads that you are going to put later in the same load case and run both of them together. Okay, that's what's going to happen. Okay, let's say we are done with the dead load. Let's modify live load. So, let's add a new load pattern, which is the live load. Why? Because I have here 2 load patterns, dead load and live load. All right, so I'm gonna come here, I'm gonna name live. And I'm gonna name this load pattern live. And I'm gonna make this self-weight multiplier 0 because I don't want any own weight. If you make this equal to 1, and say modify, what's gonna happen? Can you guys tell me? 2 times, but everyone in a separate load case. So basically, SAP 2000 is gonna calculate the own weight and run it in the dead load case, and it's gonna make the own weight is run in the live load case. By the way, SAP 2000 only run case by case. He cannot combine the cases unless you tell him to combine cases. So SAP 2000 is going to run the dead load separately from the live load. So he's going to calculate the own weight. Okay? So I'm going to keep it 0. And I'm going to modify. And then I'm going to say, okay, right now I defined all the load patterns that I have. So right now I'm ready to start drawing the structure because I already defined the sections. And I'm ready to assign the load on the structure because I already defined the load patterns. Okay? I couldn't do this from first place without defining all these systems. I can do them, but it's gonna cost me a lot of time down the road to define these things again. All right, so let's see what we can do next. Next is to draw the structure. You can draw the structure using multiple things here. You can use this tools on the side. Here, if you want to draw a point. Here, if you want to draw a frame member. This is also drawing frame members, but in different ways. I'm going to teach you what is the difference. And this is also drawing a shell, like a slab or something, using different ways. What is the difference between them? So this one, if you want to draw a point, you just click on the point. It's going to draw a point. Sometimes you want to draw a frame member from here to here. So you just make a point here and a point here, and you draw a frame member between them. This is drawing a frame member between 2 points. This is like by one click, if I click on this grid, like if I use this one, the one that has a frame and with a point in the middle, I just click on this grid, it's gonna draw a frame in between the 2 points in the grid. So let's see the difference. I'm gonna come here, I'm gonna click on this frame. Once I click on this frame, it's gonna open a box. It's called the properties of the object. And it asks me, what is the section type that I wanna use? So I have an I-beam 500 and a beam 25 by 7. I can use either. So let's say I'm gonna make a concrete truss. So I beg the cross section, if you didn't define these cross sections, SAP 2000 is gonna develop his own cross section. Okay, so right now I'm ready to draw. Like once I finished here, I can look, pick this point and go to the next point and draw a frame. And I can keep continuing. So that's one way to draw. There's another way to draw. I can click on this one and it's gonna ask me again, what is the dimension? So look at this. If I click on this grid, it's gonna draw a frame in this grid. All right, if I click on this one, it's gonna draw a frame here. So let's get back to this one. This one is only, you have to select the start and the end point of the truss. Did you guys understand the difference? Okay, so right now I want to draw the members, the inclined members. Does that big tool is gonna work?
No.
Because there's no grid, right? So I only have to pick the start and the end point. So I'm not gonna do this one. This is called quick draw frame. This one is draw frame. So I'm gonna just make this one, and let's say this one, I believe this is the fastest way to do it. Oh, sorry. I can do Control Z if I did something wrong, and I can start again. And the thing is, let's say if I click this K, it's gonna get me out of the whole drawing tool. So I have to go and click on draw frame again. So if you wanna, like right now, I wanna escape this point so I can pick this point and draw another one. So you just do a right click. Look, I'm gonna make a right click. The right click didn't get me out of the drawing command, and I still can draw. All right, so right now I wanna do a right click and make something, I think it draws something that is not this one. This one I want to delete it, so I click on it and I delete it. And I want to draw another one here, like this. And now let's check the truss that we have. So we have all the members are drawn. You guys got that?
Yep.
All right. Let's say I want to delete this member. So basically you make a box. This box, if you make it from top to bottom, like if you make something like this, is gonna select every complete member inside the box. Look, I make a box from here and it goes out like this. It selects everything that is complete inside the box. Like it didn't select this member or this member or this member. But if I reverse the selection, like if I made the selection from top to bottom like this, it's gonna select anything that this box is touching. Look at the difference.
Yep.
Here, it selected everything that is complete. This one is select everything that is touching. And that's really, really important tool. Like sometimes, I want to delete these members. So I just deleted these members. And if I want to draw them again, I can draw them one piece. I draw them like this. However, drawing them that way, it's gonna make an error down the stream, but we are gonna learn from this error. I have to draw them separately and I have to do some stuff, but let's keep it as a one member and see what is gonna happen. All right? All right, so right now the geometry is ready. So what is the next step? What do you think is the next step? Is this structure ready for analysis?
Apply supports.
It supports. So this thing by itself is unstable. Once you put the load and run the analysis, it's gonna have deformation of a millimeter because the thing is gonna flip away, like it's gonna be unstable. Okay, so I wanna put the support. So basically, you select the point that you wanna put support at. Let me check here. I have roller on the left, hinge on the right. Okay, so I'm gonna get back to SAP 2000. Look at this. Here, I can select that way or I can select that way. Either is fine. Let's make escape. Look, I'm selecting it that way. But you would tell me if you assign a roller, this is not only a joint, that's a frame. But the thing is, only rollers, hinge, fixation only get assigned on points, not frames. So it doesn't matter if you select the point with other frames. But if you select this point with this point, it's gonna assign hinge here and hinge here. So it doesn't matter if you select it with frames or not. So I'm select the point and I'm gonna do something that's called assign. And I'm gonna assign joint, and this joint has something that's called restraints. So if you wanna assign a boundary condition, you go assign, joint, and then restraints. When you go to restraints, it's gonna ask you, basically you you can pick one of these figures. If you want to make it free, pick this one. If you want to make ruler, you'll tell me, why would I pick free? Sometimes you assign a boundary condition and then you figure out, oh, I shouldn't have put a hinge here. So you want to make it free. So you come here and free this support. Okay, and you can assign a ruler, hinge, or a fixation. Or you can do the restraints from here. So then, since this is a ruler, and the ruler is going to allow this structure to move in the X direction, do you think which translation that we are going to restrict?
It's the Y.
Sorry. Okay. So basically, translation 1 is the X, translation 2 is the Y, translation 3 is the Z. So if you want this point to move only in the X direction, so you are gonna, the only restraint that you have when you have a roller is the vertical. Okay? But the thing is, since this is a 2D, so we only need just the vertical is restrained, but the roller is allowed to move in the X direction. So basically you can pick the restraint or you can pick the translation. Look what is happening if I pick the roller. Roller, it says restraint from joint to local direction only in 3. So basically this joint is gonna only have a restriction to move up, but it can roll in the X and it can roll in the Y. It can rotate about X, about Y, about Z. Okay, that's the only thing that we have. So if you pick hinge, so the translations, all the translation, because hinge doesn't allow the point to move either, X, Y, and Z. Right now things 3D, not 2D. Okay? If you put fixation, everything is restrained. This is fixed. This point can move X, cannot move Y, cannot move Z, cannot rotate about any of the direction. It's fixed. All right? Okay, so I'm gonna go and pick roller and say apply. All right, so right now we have a roller. I'm still in the same option, so I'm gonna pick this point. You can select it like this, and I'm gonna assign hinge, and I'm gonna say apply. Okay, so I put a hinge. So right now, my structure as a geometry is ready for assigning the loads. So let's assign the loads. First, I said that we have dead loads and live loads. So let's do the dead loads first. So I'm gonna look at what dead loads that I have at 4.2 and 5.5, 4.2. So what I'm gonna do, I'm gonna come here and I'm gonna select the points that have the same load value, this one and this one. And when you select this, you will find something down here. It says how many joints are selected. It says 2 points selected. And I'm gonna go back to assign. Assign is always for assigning loads, assigning restraints, assigning sections. All these you can do it from that side. Right now, I wanna assign. At first, when we define the frames, and I drew the frame, I told you if you didn't define the frames, the SAT 2000 is gonna assign its own frame, right? But let's say down the road, you wanted to change the frame section. We made this frame section concrete. Let's say you want to make them steel. You can select them and assign a new frame or assign a new shell. So you can do that. But right now, I don't want to assign a frame property. I want to assign a frame load or a joint load. So you would come here to assign, and I'm going to assign something called joint load, and I want to assign forces. So when you click on forces, it's going to open a box, and it's going to ask you in the box, what is the load pattern? So I'm gonna say the load pattern is dead. It's a dead load. And here it's gonna ask you about the direction of the dead load. So it's gonna ask you, is it in the X global, Y global, Z global? Where do you wanna assign this load? So this load was going down. So in which direction this load is gonna be? Z. And what is the sign of the load? Negative or positive? Negative. So the load value, do you guys remember? Was 4.2. So I'm gonna get in Z and I'm gonna put negative 4.2. And it says here, do you wanna add to existing load? Like let's say that you have a load on this joint 2. No, I don't wanna add it to 2. If there's 2, replace it with the negative 4.2. So I always have replace existing loads, just in case. And then I'm gonna say apply. When I apply, the load is gonna show up here, 4.2. Then I'm gonna select this joint, and I'm gonna come here and assign different value of the load, which is 5.5. So I'm gonna say negative 5.5, and I'm gonna hit apply. All right, so we put all the dead loads here. I keep this open, and I keep selecting and selecting and assign until I finish them. We have a live load here, and it's going in the X direction. So I can exchange this from dead to live. Let's check the value of the live load. It's 5 ton. So I'm gonna make this point, and I'm gonna change this to live load. And where should I put it here? First, I have to make this 0. And is it positive or negative? Positive. I'm gonna make it 5, and I'm gonna hit OK. So what happened right now? Where's the other loads? As I said, SAP 2000 only can deal with one load pattern and can only visualize one load pattern at a time. So if you assign a live load, look what happened here. It says joint load and it's live. So it only shows the live load. Where's the dead load? Is it gone? No, it's not gone. It's saved, but it's not visualized. If you want to visualize the dead load, so you would come here to view, display, and then in display you would show object load assigned, and then you would go to joint, and then you change from live to dead, and you say OK. So it's going to show you the dead load. Where's the live load? The live load is there, but not visualized. So it's there, it's not visualized. If you want to visualize it, you have to visualize it yourself.
Can you do again that step because the screen went dark?
Oh. Okay, so you go to display here, and then you go, after display, you go to object load assigned, and then you would go to joint, and in joint you check which load pattern that you want to see. So if I want to check live, I'm going to say OK, it's going to show me the live load. Perfect. Okay, so I have all the loads, all the geometry, all the boundary conditions. Everything's ready, right? However, this is not right. There's some tweaks that we need to do so that we can make this truss actually represent the truss that we are solving. But let's see if we run it that way, how is the final results is going to look like, and you are going to tell me why that happened, all right? Okay, so the thing is, I didn't save the model, so one of the most important things that you have to remember is to save the model, because sometimes things happen, you work for 4 or 5 hours and everything's gone. And also try to save it in a folder. If you save it on your desktop or in an open space in your computer, it has hundreds of files. So your desktop is gonna be bombarded with a lot of files. So you always keep it in one file. So I'm gonna name it truss, and I'm gonna say save, and definitely it's safe. The thing is, it has a file for the geometry, a file for the load pattern, a file for everything. So you don't want all these files to be in your desktop. You have to have it in a specific folder under a specific name. So right now we say, let's run the analysis and see how we can get results. So you can come here to something that's called analyze here, and you can say run analysis, or you can click on this button, this small arrow, run the analysis. When you run the analysis, it's gonna ask you a few questions. What are these questions? Is it going to ask you, do you want to run all these load cases? Do you want to run the dead and the live? And there's a load case is called model, which is a vibration case we use for seismic, and we don't need it right now. And it takes more time than these two. So what I'm going to do, I'm going to escape the model. I'm going to say, don't run model. And I'm going to say, don't run. Actually, I said don't run all. So I'm going to say, don't run this case. And I'm going to say, run this case. And then I'm gonna hit run now. It's gonna take a minute. And then once it's run, all what we need to learn how we can show the results. All right, so this is our truss, right? Looks cool, huh?
How very cool.
This is actually not the actual deformation that this truss is gonna have in real life, but it actually shows you a little bit of so that you can imagine, right? So let's see what happened here. If you want to show like the deformed shape, like you can hit here on a start animation. So this is how the truss is going to look like. However, this is under the dead load. This is under the dead load only. If you want to show under the live load, you would come here to display, and then you would show deformed shape. And in deformed shape, you say, I want to show the deformed shape under live load. And I'm going to hit OK. And that actually makes sense. All right, the thing is, start animation only do in 3D. In 2D, if you are in a 2D mood, like it's not going to show you. Like here, no, it can't show in 2D. The thing is, start animation, it needs to be in a deformed shape mode here. So if you click on this screen, this start animation is going to be gone. So you have to be in the deformed shape mode. Like when I was here, look, I clicked here, it's not here. I only have to click here, and once I click here, I can start animation. And that makes sense. For live load, when you have a load is going that way, it's going to make the truss going that way.
Why does it go back and forth?
Because it shows you, like it only goes backward, but it shows you like animation, repeated one. Like this is how the live load is going to go. All right? But this is not going to happen in real life. In real life, it's going to be pushed that way, but it's just showing you as an animation visualization thing. Like this is how the truss is going to move. All right? Okay. So let's see how we can subtract bending moment and shear force and normal force. This is a truss. What is the internal force in this? It's supposed to be in this truss.
Actual.
What?
Only normal.
Only normal force, right? That's a truss. It doesn't have shear. It doesn't have a moment. So let's check that. So you can go, by the way, you can show the deformed shape from here. Like this, if you click on this, it's going to show undeformed shape. If you click on this, it's going to show deformed shape. You say, I want to see deformed shape from dead load. You can click dead load, and then you say OK. If you want to show internal forces, you click on this one. And internal forces, you can show, because this is a truss, you only can show joint reaction and frames. There is no shells, there is no solids, there is no plane, only reactions and member forces. So let's say, what is the reaction at the joints? I'm going to click on this. It's going to ask me, do you want the reactions from the dead or the live? I'm going to ask, I want them from the dead, and I'm going to say OK. So it's going to show you, here's 2 reactions, here's 1 reaction. If you want to show reactions from the live load, so I'm going to hit live load, I'm going to hit OK. And actually that makes sense. If you have a 5-ton goes that way, this is the only one that can take the 5, and these 2 is going to make a moment like this, so this is going to counter the moment, and they are equal in value. Okay, so reactions make sense. Let's see the internal forces. All right, I'm going to see the internal forces in the frames, and I'm going to show them due to the dead load. Here it asks you, what internal forces do you want to see? Do you want to see axial force, like normal force? Or you want to see shear 2-2 and shear 3-3 and moment 2-2 and moment 3-3. Do you guys remember? I told you our cross sections is like this, and this is the directions. I believe it was 1, 2, and 3. So we only interested in Q3 in the 3 direction and the moment around 2, right? Okay. So let's see what we have here. First, let's see the axial force. I'm gonna say OK, and this is the axial force. The axial force makes sense. If this truss bended that way, this is gonna be under tension, which is blue, and these are gonna be under compression, which is red, right? And this one is gonna compress also as well. These 2 and these 2. You know, if these 2 was that way, like not that way, it's gonna have a tension, not compression. But because they are all that way, they all have compression. All right. Okay, so let's see. It's supposed to be, if I clicked on shear moment 2-2 or shear 3-3, they're supposed to be 0. So let's see what's gonna happen. Oh, sorry. It's supposed to be moment M. All right. Sounds like the cross sections should be, this is 1. And this is 2, and this is 3. So this is the moment about 3. I'm not sure. Maybe you guys check the notes. I believe it's 1, 2, and 3. So this is the moment around 3. So that's a bending moment. let's focus on that. Is that right? Like we have a truss that has a bending moment? That's not right. However, when we draw the truss, we draw it in a way that can develop a bending moment. Do you guys know how that happened?
Probably the whole beam.
Okay, that's one thing.
For the releases.
Releases. The thing is, excellent. When you drew this, how the truss is gonna know by itself if it's a frame and this point should have a bending moment. In truss, every one of these points is like an intermediate hinge, has a moment equal to 0. The thing is, when we draw this truss, these members were connected to each other, like each connection here was like this. We either move together or be together. So I have to define a special joint here to tell the truss, hey, each joint has a moment equal to 0. We didn't do that. We kept it, all of them continuous and connected. So we need to tell SAP 2000, hey, all the points here has 0 bending moment. We didn't do that. So that's one way to do it. And by the way, we also, let's keep this at the end because once we finish this, we are gonna still have more errors. So I'm gonna tell you where these errors come from. Okay, let's see how we can release the moment at the joint, how we can model an intermediate hinge at each joint. So I have to unlock the model, so I can't do the edit. So I'm gonna unlock, and I'm gonna select all the joints that I have here. I selected all the joints. And I'm gonna make something it's called assign joint frames, sorry. And there is something in frames that's called release and partial fixity. Okay? So what is release and partial fixity? Basically, we can tell SAP 2000, hey, I wanna release all the moment here. I wanna make the stiffness of this joint equal to 0. Okay, so we can do this for every joint. However, let's say that you have a spring and you don't want to have this joint have 0 moment. There's a little bit of rigidity. You have to calculate the stiffness of the spring and you can find the value of the partial fixity. See, frame partial fixity spring. So if you want to say that you have these joints are free, you have to make the partial fixity stiffness equal to 0. But if you have a spring, and this spring is holding these two together, you have to put the stiffness of the spring here. So let's say that the resistance of each joint to the moment MS3C at the start is equal to 0, at the end equal to 0. And look at the values of the moment here, or the resistance. It is ton force meter per radian, which is the unit of a spring stiffness, rotational spring stiffness. Okay? So basically, if you have a spring holding if you want to solve the structures that we have with the springs, you have to put the spring stiffness here at the start and the end. Okay? All right. So let's put this, and I'm gonna hit OK. So all what I did, let's go again. What do you think about this? Do we miss something? Is that right? So basically, make the moment 0, 0, 0, 0. All the moments here are gonna be 0. Are we ready to run the analysis?
No, the bottom.
The bottom, what is the wrong with the bottom? The thing is, it's only gonna make the moment equal to 0 here and 0 here, but in the middle, it's not gonna be 0. This is gonna take moment and this is gonna take moment. Okay, so I'm gonna change it for now. Maybe you run it home and see what's gonna happen. If we keep it that way, I'm gonna hit F4. F4 basically show the undeformed shape, or you can click on this one. And I'm gonna click on this frame and these 3 points. And I'm gonna say edit lines and divide frames. And I'm gonna say break at the intersection with the joints. So it's gonna break this frame at the joints that I selected. Here, everyone is gonna be separate. And I have to do the assign again. I'm gonna select all of them and assign frame, release and partial fixity, and I'm gonna make all of them are equal to 0. So right now, this frame is right. So let's run the analysis and see what is gonna happen. Run now. So right now, all the moments are equal to 0 at all the joints, right? Here's the moment is equal to 0. Here's the moment is equal to 0. However, there is a bending moment at all the frame. Why is that? Why do we have bending moments like this?
Self-weight.
Self-weight. Because every joint has a moment equal to 0, But the thing is, the beam is bending under its own self-weight and is giving you this bending moment. Do you guys get that? Thing is, yeah, we define every joint is equal to 0. That means that every single truss member right now is acting like a simple beam. But the only way to make it not acting as a simple beam is to eliminate the self-weight. Let me tell you something. A truss member is like a link member, something like this. That's a truss member, and let's say you have something like this. If this has loads like this, all the loads at the joint, that structure is called truss. But once you have a load in the middle between the two hinges, this structure is not truss anymore. That is acting like a frame. If a member is taking bending moment and shear force, that's not a truss member. That's like a frame. So if all your load is at the hinges, like this, and there is no load in between, and the member has an intermediate hinge at the start and the end, that is called a truss member. But once you put a load in between, that's not a truss member anymore. And if you guys remember, we had something like this, a frame, and I told you there's something called a link member that only have one vertical reaction, something like this. But this is not gonna be a link member. Link member is a truss member. This is a link member, but if this link member has a load like this, that's not a link member anymore. That's a frame member. Why? Because right now you are gonna have a reaction that way, and this is gonna act like a frame, and it's gonna have a bending moment like this, so it's gonna be different. All right, so how we can solve this? We are gonna go back to the on weight that we defined. I'm gonna unlock the model, and I'm gonna go back to define load patterns, and I'm gonna make the self-weight modifier equal to 0 for the dead load. And then I'm going to modify, and I'm gonna hit OK. And let's rerun the analysis and see what is gonna happen. Run now. Actually, it runs, and there's no bending moment. It says I'm showing bending moment M33. There's no bending moment. So we solved the issue of the hinges. We solved the issue of the bending moment. So that's right now a pure truss. Doesn't have a bending moment M33. Moment about the 3 axes. Okay, so if you want to show the shear force, you can come here and show frame and cables and show the shear 2-2. And the shear 2-2 also is going to be 0. There is no shear. Only there is axial force. So I'm going to show an axial force, and then I'm going to hit OK. And this is the axial force that we have. And the thing is, once you come here, it's going to tell you what is the actual axial force. That's 6.6 ton. If you go up, it's going to tell you it's a negative. And here you can click on the member, and the thing is, if there's a variability in the tension or the compression, is going to show you and tell you here what is the actual tension of this member. All right, so this is due to the dead load. What if you want to show this due to the live load? So let's say I'm going to hit here live load, and I'm going to say okay. So that is how the straining action due to the live load. What if you want to show this due to both dead and live at the same time? I told you we can't, but we can do something called load combinations. So how we can do these combinations? So the combinations, I'm gonna go to define load combinations, and I'm gonna add new load combo. So I'm gonna make a comp 1, and we can say, like, the thing is, when we design structure, we don't design them for load patterns separately, because live load and dead load and seismic, they all come together. Dead load and live load, they mostly are together. But we do load cases, like we do one with seismic without wind, one with wind without seismic, one with wind and seismic, but we reduce their factors. One with rain, not with a snow, and one with roof life load without rain. So we do lots of load combinations that are coming from space. So you have, actually, when you design structure, you have to do all these load combinations. I remember when we used to design building, you can have like up to 50 load combinations. And your cross section have to pass all these load combinations. If it failed one of them, so you have to change the cross section. Okay? So let's do one load combination. Let's say comp 1, and I'm gonna make the dead load is 1, and I'm gonna make the live load, for example, let's actually make this 1.4.
11.
And then I'm gonna say modify, and I'm gonna make, sorry, I wanna make the dead 2, and let's make the dead as 1.6. I'm gonna say okay, Okay. The good thing about the load combination, you don't have to unlock the model to do it. You can keep the model in the run, and you can do the load combination. So right now, you can, in the visualization here, you can come to frame loads, and you can change this from live to comp1, and I'm gonna show the axial forces, and it's gonna show me how's the axial forces look like. So this is the axial forces due to a combination of the dead load and the live load. Let's see if you want to show the deformation. You can show also the deformation from the load combination number 1. And I'm going to also say okay. And here's it shows you how does the deformed shape look like right now. You will tell me, oh, where's the live load? The thing is, the live load was a little bit smaller than the dead load, so it doesn't show like how is the structure is moving that way that much, but it's still there. Okay? All right, so that's what we have for now. To be honest, I explained everything about SAP 2000 in this example in 1.5 hours. So next time we're gonna solve maybe 3 different problems. Every one is gonna take 15 minutes or something. We're gonna do a beam, we're gonna do a frame. So maybe we're also gonna do a slab because we already covered the basics. Most of the tasks, edit, view, define, assign, analyze, and also display. So we covered many things. So we have like 2 lectures on SAP 2000 to cover the rest of the stuff, right? All right, sounds good. See you guys next time.
Thank you.
Thanks.